Hello guys, myself Assistant Professor Gaurang Prajapati from Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. Today I am going to cover the chapter of Column and Struts of the subject Structural Analysis 1, 4th Sem Civil Engineering. Okay, so first of all, let's see the weightage of the chapter, that is Column and Strut, in all the previous examples of GTU. Okay, on an average the weightage of this chapter is 11 marks. This is the theoretical criteria of the chapter which have been asked in the examples. Few definitions and some of the derivations are there, while this one is the example summary of the chapter which has been asked in the exam, and these are the examples which were actually asked. Okay, I have solved at least minimum 1 or 2 examples of each and every method in this video. I will cover all the topics. Okay, so first of all, let's start with the theoretical concept. So first of all, let's understand the difference between column and strut. So first of all, let's try to understand what do you mean by strut. A structural member subjected to axial compressive force is called the strut. So strut is any structural member which is subjected to compressive force. Okay, it may be vertical, horizontal or inclined. So it can be of any, we can say, orientation, vertical, horizontal, inclined, like that. Okay, the cross section of the dimension of the struts are small. Then normally struts carry smaller compressive force, and struts are used in the roof truss and in bridge truss. Okay, so this is all about the truss. Now let's try to understand what is column. So when the strut is vertical, it is known as column. So we saw one point over here, strut can be vertical, horizontal, inclined. But over here in the column, we can say whenever the strut is vertical, it is known as column. So ultimately we can say this vertical strut is known as column. Okay, the cross section of dimensions of the column are large. Normally the columns carry heavy loads, and columns are used in the concrete and steel building. Okay, so this is the basic difference between column and strut. Okay, so it carry the light axial load and it carries the heavy compressive load. Then it may be vertical, horizontal or inclined. It is always vertical. The cross section dimension of the strut are small, while in this case column it is are quite large, and it is used in roof truss, bridge truss, while it is used in concrete and steel building. Okay, so this is the basic difference between strut and column. Then let's try to understand some of the definition which will be used during the examples. First of all, radius of gyration. We have already studied this one in the subject mechanics of solid in the chapter moment of inertia. Okay, radius of gyration. The distance from the given axis at which, if all the small elements of the lamina are placed, the mi, that means moment of inertia of the lamina above the given axis, doesn't change. This distance is called the radius of gyration. As I told you, we have already studied this one in the chapter of moment of inertia of the subject mass. So mathematically it was formula is k equals to root of I by a. We will use this formula during the examples. Okay, or if we want to convert it into in terms of I, then it will be, we can say I equals to area into k square. Unknown parameters were k, radius of gyration, I, moment of inertia, and a, that is cross section area. Next, that is slenderness ratio. Okay, slenderness ratio is defined as the ratio of effective length of column divided by minimum radius of gyration. So if I want to convert it into the formulas, then lambda equals to L by K, where L stands for effective length of column, while K minimum, that is minimum radius of gyration, that is this one, root of I by A. Okay, then over here, if lambda means slenderness ratio of the column, for the column is more, its load carrying capacity will be less, and vice versa. If the lambda for the column is less, then its load carrying capacity will be more. Okay, so remember the formula of the slenderness ratio, we will use that one also during the example. Then say column can be of two types, long column and short column. So first of all, let's try to understand the difference between them two. So when length of the column is more as compared to its cross section dimension, when length is, we can say, greater than cross section dimension, it is known as long column. Vice versa, when length of the column is less as compared to its cross section dimension, then it is known as short column. Okay, so this is the basic difference between long and short column. So there are also some of the other conditions are there. to verify, or we can say to differentiate the long and short column. So first of all, for long column, if LE by D is greater or equals to 12, or we can say lambda, that is LE by K minimum, greater or equals to 50, then it is known as long column. While for short column, if LE by D is vice versa less than 12 and lambda is less than 50, then it is short column. Unknown parameters were LE, effective length of column, D, least lateral dimension, and K minimum, minimum radius of gyration. Okay, for mild steel, if lambda is greater or equals to 80, then it is known as long column, but this one is for only mild steel. Okay, then two different kinds of loads will be there, crushing load as well as crippling load. So first of all, let's understand the crushing load. See, in case of the short column, so first of all, always remember that crushing load will be applicable to the short column first of all. So in case of the short column, with increase in axial compressive load, compressive stress increases. After some load, the column starts crushing. The load at which the short columns fail by crushing is known as crushing load, and the stress corresponding to the crushing load is known as crushing stress. So in simple word, see, whenever a short column is there, okay, whenever the load applies over it, so once we apply the load, so obviously in that case, whenever the load is increased, obviously stress will be increased, because stress equals to force divided by area. So whenever the force will be increased, obviously stress will also increase. Okay, but after some point, what happens? Column starts, or we can say column fails by crushing. So the load at which column fails, that is known as crushing load, and the stress which are corresponding to the crushing load are known as crushing stress. Okay, so crushing load always happens in terms of the short column, means in this one columns fails directly after applying the maximum load, while in case of the crippling, or we can say buckling or critical load, usually it is known as buckling load. Okay, so in case of the long column, now this one is applicable for the long column, with increase in axial compressive load, compressive stress increases. This is the common between the short column, long column, nothing difference. As load is increased, stress will definitely will be increased, because stress is directly proportional to the force. After some load, the column starts buckling, or we can say bending, and the bending stress also produces. Now what happens in case of the crushing load? After some point, whenever the load was increased, the column was directly failed because of the crushing load. Okay, now in this one, after some load, the column starts buckling. It will not fail directly, it will first of all buckle, or we can say bend, and the bending stress are also produces. Finally the columns fails by buckling. So the load at which the long column starts buckling is known as buckling load, or we can say crippling load. Okay, so that's the difference between them. So in this case, whenever a long column is there, load applies, so what happens? Stress increases. Okay, after some load, what happens? Column starts buckling, we can say like this. Okay, and after buckling, we can say it is failed, it is getting failed. So ultimately, what is the difference between crushing load and buckling load? In case of the crushing load, short columns fails directly because of the load, while in this one, in case of the long column, first of all column will buckle and then it will get filled. So that's the difference between these two load. Okay, so for the long column, direct stress is negligible as compared to the bending stress. Okay, so that is the difference between buckling and crippling load. Then the buckling of the column depends on the following factors. Say these factors are amount of load, length of column, and condition of column, cross section dimension of column, and the material of the column. So these are the criteria which usually affects the buckling of the column, or we can say buckling load. Now this is the main criteria of the chapter, that is column and condition and effective length. Okay, so over here we can see 4 different conditions are there which will be used during the examples. First of all, both ends are hinge. Okay, if any column has both hand hinge support, or we can say 2 hinge support at the corner, then its effective length will be equals to original length. So L equals to L. L stands for effective length and L stands for original length. Okay, over here in the figure you can see 2 hinge supports are there, so its effective length is also equals to the original length. This one. Second, both ends are fixed, so in this case conditions will be L equals to L by 2. As we can see over here, 2 fixed supports are there. This one is our L, okay, while this one is our LE. So LE will be equals to L by 2 when both ends are fixed. Third, one end hinge, one end fix. Okay, so one hinge fix, then other is hinge, like this. So in this case obviously this one is over L. So from the we can say hinge support, it is from the support, and over here it will be like this. So ultimately condition will be L equals to L by root 2. And last one end fix and other end free, one end fix free. So it will be like this. So this is our LE. So in this case we can say LE equals to twice L. So always remember these four conditions, because in this chapter in each and every examples one of these four conditions will be definitely be there. Okay, so you have to remember these relations between effective length and ordinal length. So let me repeat once again. Both ends are hinge, L equals to L. Both ends are fixed, L equals to L by 2. One end hinge, one end fixed, L equals to L by root 2. And fourth one end fixed, another end free, so L equals to twice L. So these are the conditions. And in the last, now we will apply two kinds of formulas, or we can say load, which will be used during the example. So for one of them, just a minute. First of all, first case, that is Euler's formula for the crippling load. Okay, this is the criteria. Now in this case, for the Euler's formula, the formula is P equals to pi square EI upon LE square, where unknown, that is pi, that is constant, then E modulus of elasticity, okay, I, that is mi, or moment of inertia, minimum moment of inertia, then P, that is Euler's crippling load, and LE, that is effective length of column. Okay, that we have seen these four cases like that. And another one, that is Ranking's formula. So Ranking's formula, PR equals to FC into A divided by 1 plus alpha into lambda square. So in this one, PR stands for Ranking's crippling load, A stands for cross section area, FC, that is actual compressive stress, which is always given in the data, alpha, Ranking's constant, that will be also given in the data, and lastly lambda, that is slenderness ratio, that is LE by K minimum. Okay, so we will show either one of these formulas in the examples. Okay, and lastly the last portion of the theoretical portion, that is assumptions of the Euler's formula. Okay, so in this one, first one, the material of the column is elastic, homogeneous and isotropic. Second, the column is long. Third, the load on the column is truly axial. Fourth, failure of the column is due to buckling. Fifth, cross section of the column is uniform throughout its length. Fifth, the Hooke's law is valid. Next, the column is straight before the application of the load. Last one, the shortening of the column due to axial compressive load is neglected. So these are the assumptions which is used during the Euler's formula. Okay, so now let's start the examples. Okay, now example number 1, find slenderness ratio for a column of 5 meter length with both ends fixed and having circular cross section with 100 mm diameter. Now what we need to calculate, first of all, slenderness ratio, that means lambda. We need to calculate lambda. Over here we can see for a column of 5 meter length. So length is 5 meter, let's convert it into mm, that is 5000 mm, with both ends fixed. So end conditions are given, both ends fixed and having circular cross section, means diameter will be there, that is 100 mm diameter. So diameter is 100. So this is the data given to us. Okay, now always remember the formula from which you will get answer. We need to calculate lambda, so lambda's formula will be this one, say LE by K minimum. So we need two unknowns, number one LE and next K. Now K means radius of gyration, so ultimately its formula will be I by A. So ultimately I will get three unknowns, LE, area and moment of inertia. These three are the unknowns which I need to calculate. Once I get all these three values, I can easily calculate lambda. Okay, so first of all, let's talk about the end condition. Both ends are fixed given to us, so on basis of that I can calculate LE. Say as both ends are fixed, we have seen in the theory that LE equals to L by 2. Now L is 5 meter, we can say 5000, so 5000 divided by 2, so ultimately I will get 2500 mm. Okay, that's LE. So first problem is solved. Now I need two values, moment of inertia and area. So as circular section is there, okay, diameter is given to us, so I can easily calculate area as well as moment of inertia. Let's calculate first of all area. Formula stands for pi by 4 d square. that is pi by 4 100 square. So I will get the answer 7853.98 mm square. Then moment of inertia, pi by 64 d raised to 4. So pi by 64 into 100 raised to 4. So answer will be 4.91 into 10 raised to 6 mm raised to 4. Okay, so once I get area and I, now I can easily calculate radius of gyration, that is k, root of I by a. I 4.91 into 10 raised to 6 and area 7853.98. By simplifying this one, I will get value of k, that is as 25 mm, that is radius of gyration. Okay, once I get the value of k and le, now I can put down these two value in the final formula of lambda. So lambda equals to le by k, le 2500, k minimum, that is 25. So ultimately I will get the answer 100 mm. Clear? So this is the first example which was asked in November 2019 in 3 marks. Okay, now moving forward, next example, example number 2. Just a minute. Yeah. Now a hollow rectangular column having outside dimension, let me draw the figure. First of all, a hollow rectangle section is there like this. Outside dimensions are 300 cross 200 mm, that is b cross d. Next, inside dimension 200 by 100 mm. So this one is the hollow rectangle section given to us. Its length is 6 meter and fixed at both ends. So end condition will be definitely there in each and every example. Length is 6 meter. Find Euler's crippling load. Now they have mentioned we need to calculate Euler's crippling load, means we need to calculate P. Take E, that is 2 into 10 raised to 5 Newton per mm square. Okay, so from this figure, first of all we need to write down the data which is given to us. So given data, outer dimension, that is 300 and 200 mm, inner dimension, that is 200 by 100 mm. Length is given to us, that is 6 meter, and conditions are given, both ends are fixed, and E, modulus of elasticity of steel, is given, that is 2 into 10 raised to 5. Okay, like that. Now ultimately P, so for that one, okay, over here one correction is there, it is 2 into 10 raised to 5, not 2.1 into 10 raised to 5. Now and we need to calculate P. So now first of all, Euler's crippling loads formula, I always say, always remember the formula from which you will get the answer. So Euler's formula is pi square EI upon LE square. So I need unknown, that is we can say I first of all and LE, these are the unknown. Okay, now talking about LE, end condition will definitely be given to us. See, both ends are fixed. So for both ends are fixed, we know that L equals to L by 2. So I will get the value of LE from this one. So first let's calculate that only. Say over here LE equals to L by 2, as both ends are fixed. So L is how much? 6000. So 6000 divided by 2, I got the answer, that is 3000. Okay, now that problem is solved. Moving forward, now next we need the value of I. So now as per the rectangle section, we can calculate moment of inertia from both axes, I-XX as well as I-YY. Okay, so I will calculate first of all I-XX. For the hollow rectangle section, the equation of I-XX, that is capital BD cube by 12 minus small bd cube by 12. Okay, so for that one, just a minute, let me draw the figure first of all over here of the hollow circular section. See, this is the hollow rectangle section given to us. Outer dimension is 300 cross 200, while inner dimensions are, just a minute, inner dimensions are 200 by 100 mm. Okay, so now first of all let's calculate I-XX, that is capital BD cube by 12 minus small bd cube by 12. Capital BD, that is 300 cross 200 cube by 12, small bd, that is 200 cross 100 cube by 12. So by simplifying this one, I will get the answer, that is 188.33 into 10 raised to 6 mm raised to 4. Then moving forward, IYY formula will be changed to now this time db cube by 12 minus small db cube by 12. We have all the dimensions, 200 into 300 cube by 12 minus inside 100 into 200 cube by 12. By simplifying this one, I will get the value of I by y. Finally, I, that is we can say minimum of Ixx, that is this one, and I by y. Okay, just a minute, this one is Ixx, this one is I by y. Finally, I equals to minimum of these two values. So obviously minimum will be 183.33 into 10 raised to 6. So you will ask, sir, in the previous example you didn't calculate Ixx, I by y. That is just because for the circular section I is common. We can say Ixx and I by y both have the same formula, pi by 64 d raised to 4. That's the reason in the previous example I didn't calculate separately Ixx, I by y. Okay, otherwise we need to always calculate Ixx, I by y and then take minimum moment of inertia for the calculation. Okay, so from this formula unknowns were, that is we can say I and LE. I have calculated both of them. So now let's solve the sum. So pi square E, that is as I told you, this one is 2 into 10 raised to 5. So 2 into 10 raised to 5. Then I, that is 183.33 into 10 raised to 6 upon LE square, that is L is how much? 3000 square. So that is 3000 square. So ultimately I got all the values. Now by simplifying this one I will get the answer 40209.5 into 10 raised to 3 Newton. Let's convert it into kilonewton, that is 40209.5 kilonewton. Okay, so that's the answer of the Euler's crippling load. Clear? Now moving forward, example number 3. Just a minute. Yeah. Say a column of size 250 mm cross 350 mm. Okay, rectangle section is given to us once again 250 by, just a minute, say 250 by 350 mm. Okay, so B250, D350. 4.2 meter length is given to us 4.2 meter. Let's convert it into mm. 4200 with its both ends are fixed. Again condition is given to us, both ends are fixed. Find load carrying capacity of the column by Euler's formula and Rankine's formula. Now in this example we need to solve the sum by both the equations, Euler's as well as Rankine's. Okay, take FC 320 Newton per mm square, that is this one. E 2.1 into 10 raised to 5 Newton per mm square, and alpha, that is 1 divided by 6.00. Always remember, whenever these values are given we need to compulsory apply, we can say Rankine's formula, because FC, alpha, these are the unknowns of Rankine's formula only. So without these two values we can never solve any example using the Rankine's formula. So these two values are necessary for the Rankine's formula. So whenever these two values are given, always try to understand that you need to calculate the sum using the Rankine's formula. E is common between both of them, in Euler's as well as in case of Rankine's also. Okay, so now first of all we need to calculate the force by using both formula. So first of all let's try to solve it using the Euler's formula. Let's talk about the known. Already in the previous example we discussed that we need two values for Euler's formula, I and LE. Okay, for LE, if n conditions will definitely will be there, that is both ends are fixed. So I can say LE equals to L by 2 when both ends are fixed. L is given to us 4200. So 4200 by 2, so I got the answer 2100 mm. Both ends are fixed. So that's the first case. Next I need I. So I equals to, we can say, minimum of Ixx, I by y. Rectangle section is there, so equation of moment of inertia will be BD cube by 12 as well as DB cube by 12 for Ixx and I by y respectively. So let's calculate first of all Ixx. BD cube by 12, B250, D350, 250 into 350 cube by 12. So I got the answer 893.23 into 10 raised to 6 mm raised to 4. Then I by y, that is DB cube by 12. So 350 into 250 cube by 12, I got the answer 455.73 into 10 raised to 6. So finally I equals to minimum of Ixx as well as I by y. So obviously minimum will be this one. So 455.73 into 10 raised to 6 mm raised to 4. So once I get the value of I and LE, now I can easily calculate the Euler's formula. Let's apply the Euler's formula. That is, formula stands for pi square EI upon LE square. Say pi square E, that is given to us in the data 2.1 into 10 raised to 5. then I, that is this one, 455.73 into 10 raised to 6, and LE, that is 2100, that is 2100 square. By simplifying this one, I will get the answer 214,184.12 into 10 raised to 3 Newton. Let's convert it into kilonewton. 214,184.12 kilonewton. So this is the exact method which we used in the previous example, but in this example they have told us to calculate the load using Rankins formula as well. So now I will go for the Rankins formula. Okay, now for Rankins formula, just a minute, let me keep it in one frame because I will need the value. Now Rankins formula, that is formula is this one, PR equals to FC into A divided by 1 plus alpha into lambda square. Now let's talk about unknown. First of all, two constants will be there, that is FC and alpha, that will be always given in the data. FC over here 320 Newton per mm square, and alpha that is also given to us, that is 1 divided by 6,400. Okay, so these two problems are solved, it is always given in the data. Now the unknown parameters will be area and lambda. These are the two criteria which we need to solve to use the Rankins formula. Now talking about area and lambda, area we can easily get a rectangle section, that is we can say B cross D, and lambda, so for that one we need to apply the formula, that is slenderness ratio LE by K. Now LE we have already have. Now talking about K, radius of gyration, so for that one we need two values, root of I by A. So we need to calculate area, which we will already calculate over here, and I, which is I have already calculated in the previous EULER'S formula. Okay, so hope so you get it. First of all, always calculate the unknown parameters and then you can go for the final formula. So first of all, I need to calculate the unknown area, so I will calculate first of all area for the rectangle section. Area cross, area means B cross D, B and D are given to us 250 cross 350. I will easily get the area. Answer will be 25 cross 350, so answer is 875.00 mm square. So first of all I got the area. Now in order to get the lambda, first of all I need to calculate K, that is radius of gyration, root of I by A. I already have the value of I and already have the value of A, so I can easily calculate K, radius of gyration, that is root of I by A. I, that is 455.73 into 10 raised to 6, and area, that is over here 87500. So ultimately I will get the value of K, that is 72.17 mm, this one. Okay, once I get area and K, now I can calculate lambda. Lambda stands for LE by K. LE we have already calculated over here 2100, and K we have calculated over here 72.17. So I will get the value of lambda, that is 29.1. Once I get this value, now I can apply the final formula. Okay, just a minute. Yeah, so now the formula stands for PR equals to FC into area divided by 1 plus alpha into lambda square. So first of all FC, it is given to us in the data 320 Newton per mm square, 320 Newton per mm square. Area we have calculated over here 87500, so multiply by 87500 divided by 1 plus alpha is given to us 1 divided by 6400, so 1 divided by 6400 plus lambda square, that is 29.1, so 29.1 square. Clear? So by simplifying this term I will get the answer, that is 24728.43 into 10 raised to 3 Newton. Let's convert it into kilonewton, that is 24728.43 kilonewton. Okay, so that's the final answer of the Rankins formula. Okay, so whenever sum comes under the Rankins formula, you will always have to do this one. You need to calculate area and lambda, and in order to get the lambda, first of all you need to calculate radius of gyration, that is for that one you need I and A. Okay, and in order to get the lambda you will need also value L, like that. Okay, so this was the common sum in which we use both of formulas, EULER'S as well as Rankins. Okay, let's solve some of the other sums also like this which have been asked in the exam. Example number 4. Fine. See, previous example was, this is, see, this example is of rectangle section which we have solved, example number 3. Now let's solve same kind of example but the of different cross section. Now in this one, example number 4, just a minute. Yeah, see, find load carrying capacity of the column having circular cross section. Now this time I am using the section circular, while in the previous example, in example number 3, we calculated the sum of the rectangle section. Now this one is circular section with 400 mm diameter by Euler's formula and Ranking's formula. Okay, the column is 6 meter long, so length is 6 meter, say 6000 mm, fixed at one end and each and other end. So condition is given to us. Take Fc equals to 320 Newton per mm square, E2 into 10 raised to 5 and alpha. All three constants are there, Fc, E and alpha, and we need to calculate P and PR. Okay, that is Euler's formula and Ranking's formula. So first of all, for Euler's formula we know that we need two unknowns, Le and I. Okay, so first of all let's start it with the Le. N condition is given, one end fixed, other end hinge. So for Le, for one end fixed and other end hinge, formula will be L by root 2. L is given to us, that is 6000 divided by root 2. I will get the answer 4242.64 mm. So problem of L is solved. Now next, that is I. Now as circular section is given, so Ixx and Iy formula will be common, that is pi by 64 d raised to 4. Diameter is 400 mm, so pi by 64 into 400 raised to 4, I will get the I, that is 1256.64 into 10 raised to 6 mm raised to 4. So once I get Le and I, now I can calculate Euler's formula. So let's apply Euler's formula. Pi square Ei upon Le square, pi square E, that is constant, 2 into 10 raised to 5, I, that is 1256.64 into 10 raised to 6 upon Le square, that is 4242.64 square. Okay, then by solving this one I will get the answer 137805.67 into 10 raised to 3 Newton. Let's convert it into kilonewton, 137805.67 kilonewton. Okay, so this one was of Euler's formula. Now for Ranking's formula, so as we discussed in the previous example, this one is our formula, Fc into A divided by 1 plus alpha into lambda square. So for that one, first of all we need area. Now for the circular section, the equation of area stands for pi by 4 d square. Diameter is 400. Okay, so pi by 4 into 400 square, so I will get the answer 125663.71 mm square. So problem of area is solved. Then in order to get the lambda, first of all I need to calculate K, radius of gyration. Formula stands for I by A. Okay, radius of gyration, that is I by I is already calculated over here, that is 1256.64 into 10 raised to 6, and area is this one, that is 125663.71. By simplifying this one I will get the K, that is 100. Once I get the value of K, let's solve the lambda. For that one we need the value of Le. Le is over here, you can see 4242.64. okay, so let's solve it. Lambda Le by K, Le 4242.64 and K, that is 100. So ultimately I will get the value of lambda 42.43. okay, once I get the value of lambda, we have two unknowns, Fc and alpha, which is directly given in the data. Now I apply for the final formula. Okay, so just a minute. So applying Ranking's formula, PR equals to Fc into area divided by 1 plus alpha into lambda square. So first of all, talking about Fc, 320 Newton per mm square. Okay, so 320 Newton per mm square. Area 1256.63.71, that is over here, divided by 1 plus alpha, that is 1 divided by 6400, and lambda, that is 42.43 square. Okay, by simplifying this term I will get the answer 31385.28 into 10 raised to 3 Newton. Let's convert it into kilonewton, 31385.28 kilonewton. Clear? So this is the answer. Okay, now next term. So in the example number 3, as I told you, we solve the sum using Ranking's as well as Euler's formula of the rectangle section, while in the example number 4 we solve the sum of the circular section. Now in example number 5, let's take another kind of section. Just a minute. Yeah, see, a hollow cast iron column. Say now this one is hollow cast iron column of the outside diameter and thickness, means circular section is there, hollow circular section like this. Okay, sorry, my figure is somewhat rough, like this. Hollow circular section is there. Outside diameter is, we can say, outside diameter d, that is 200, and thickness that is given to us, this thickness stands for 20 mm. Okay, so this will also be thickness t, that is 20. So ultimately, if we are concerned about inside diameter, means if we are concerned about inside diameter small d, then it will be capital D minus 2 times thickness. Capital D is 200, thickness is 20, so ultimately small d will be, we can say, 160 mm. Okay, so you can see over capital D 200, thickness 20, so small d equals to d minus twice t, that is 160 mm. Next, it is 4.5 meter long, so length is given to us 4.5 meter, so 4500 mm, and it is fixed at both ends. So end condition is given to us, both end fixed. Calculate Euler's and Ranking's safe load. Now this time they have mentioned the safe load. Safe load is nothing, we can say any safe load means, for example, Euler's. So Euler's formula divide by factor of safety. Now for safe load, you must need the value of the factor of safety, that will be given to us in the data. Okay, for cast iron, FC 550 Newton per mm square, alpha 1 divided by 1600, E, that is 0.8 into 10 raised to 5, and FOS, that is taken as 3. See, FOS is given to us, and we need to calculate safe load in both cases. So in case of safe load also, we will calculate the regular load, that is P and PR, and then what we will do for safe load, we will divide them with factor of safety. Okay, that's the only difference between those two. Okay, now as we all know, for Euler's formula we need two unknown, LE and I. So first of all, LE, end condition will be given to us, both ends are fixed and length is 4500. So first of all, LE, for both ends fixed, LE equals to L by 2. L is 4500, 4500 divided by 2, so I got the answer 2250. So first problem is solved, that is of LE. Now let's solve the unknown, that is I. Now for the hollow circular section, moment of inertia for Ixx as well as Iy, same formula will be there, pi by 64 d raised to 4. Okay, let's put down the value. Pi by 64, capital D is 200, small d is 160. Let's put down the value, pi by 64, 200 is to 4 minus 160 is to 4. So I will get the answer 46.37 into 10 raised to 6 mm raised to 4. So I got the answer of I. Okay, so now let's solve the Euler's formula. See, pi square EI upon LE square, pi square E, that is given to us 0.8 into 10 raised to 5, I, that is 46.37 into 10 raised to 6 upon LE, that is, we can say, 2250 square. So ultimately I will get the answer, that is 7232.04 into 10 raised to 3 Newton. Let's convert it into kilonewton. 7232.04 kilonewton. Now if we were asked to calculate only Euler's load, then our sum will be close over here for the Euler's load. But they have asked us to calculate the safe load, then safe load will be Euler's load divided by factor of safety. Euler's load, that is this one, 7232.04, and factor of safety is given to us, that is 3. So by 3. So ultimately we will get the answer, that is 2410.68 kilonewton. So this is the safe load for the Euler's formula. Okay, now we need to do the same thing for the Ranking's formula. So let's apply the Ranking's formula. PR equals to FC into area divided by 1 plus alpha into lambda square. Talking about unknown, we have already solved this kind of example. First of all, we need to calculate the area. For the hollow circular section, the equation for the area stands for pi by 4 capital D square minus small d square. We already have the value of capital D 200, small d 160. Let's put down the value, pi by 4, 200 raised to 4 minus 160 raised to 4. So ultimately I will get the answer, that is 11309.73 mm square. So first problem is solved of the area. Now we have the value of I as well as over here. See, 46.37. So let's calculate k, root of I by a. Okay, to get the value of lambda. Say I 46.37 into 10 raised to 6, and area, that is this one, 11309.73. So ultimately by solving this one I will get the answer 64.03 mm. That's the value of k. And once I get the value of k, just a minute, yeah, once I get the value of k, now I can easily calculate lambda, LE by k. Let me see how much LE is. LE is 2250. Okay, so let's put down the value over here. Now LE, that is 2250, and k 64.03. So I will get the answer 35.14. Okay, that's the answer of the lambda. Now let's calculate the Rankins formula. First of all, this one formula stands for FC into area divided by 1 plus alpha into lambda square. FC, that is given to us 550. So 550 area, that is 11309.73, divided by 1 plus alpha, that is 1 divided by 1600, and lambda, that is 35.14 square. By simplifying this one I will get the answer 3510.91 into 10 raised to 3, and let's convert it into kilonewton. 3510.91 in kilonewton. And then for safe load we will get Rankins formula divided by factor of safety. Factor of safety is 3, so I will get the final answer, that is 1170.3 kilonewton. So what we have learned in this example, whenever you have been asked to calculate safe load, then we need to calculate the original load and then just divide them with the factor of safety. Factor of safety will always be given to us in this kind of cases. Okay, so in the previous 3 examples we have, first of all, in example number 3 we got rectangle section, in example number 4 we solved the circular section, and in example number 5 we solved the hollow circular section. In all these 3 cases we have solved Euler's load as well as Rankins load, and in this one we have calculated safe load also in both cases. Okay, so hope so your concept about the Euler's as well as Rankins formula is clear now. Okay, now let's calculate some of the sums which are variable in this kind of examples. Example number 6, a hollow circular pipe having internal diameter 300 mm and thickness 40 mm. See, a hollow circular section is there. Okay, just a minute, yeah, hollow circular section is there. Now in this one, say internal diameter small d, okay, that is 300. Then thickness is given to us 40 mm. This one is our thickness 40 mm. So if we are concerned about, we can say this capital D, then internal thickness plus 2 times twice thickness, right? Internal 300 plus 2 times 40. So ultimately I will get, we can say, I am writing over here, that is 380 mm. Okay, so small d 300, d 40, capital D, that is this one, 300 plus 2 times 40, we can say 380 mm. Now let's move. Okay, you can see over here. Now next, moving forward, it is used as a column. Okay, no problem. Find critical load using Rankins formula. Now they have mentioned for this one we need to completely use Rankins formula only. Now as we are solving the sum using the Rankins formula, so we need unknown FC and alpha. FC is given to us, that is 320 MPa, alpha 1 divided by 4800, and slenderness ratio is given to us. Now normally slenderness ratio is never given to us, in this example it is given, that is 90. So slenderness ratio is 90 FC, and we can say alpha, this one is alpha 1 divided by 4800. What will be the length of the column if it is fixed at one end and free at other end? So in this example length is unknown to us. See, normally length is given to us, okay, and we calculate the forces, but in this example now as you can see length is unknown to us and they have given us lambda. Okay, so whenever this kind of sum happens, okay, so first of all let me see what they have given to us. They have given to us lambda, all the circular dimensions, okay, and all the unknowns FC and alpha. So first of all let me apply Rankins formula, and then let's see what the unknown parameter stands for. Say if I am applying Rankins formula, unknown will be, as we discussed earlier also, area I LE. From I and area I will get the value of k, and from k I will get the value of lambda, like that. But in this example lambda is already given to us, so there is no problem with the lambda. So I can directly calculate first of all lambda's formula. Only I need to calculate the unknown, that is area. Now for the hollow circular section, formula for area stands for pi by 4 capital D square minus small d square. Capital D 380, small d 300. So pi by 4 380 square minus 300 square. So ultimately I will get the answer 42725.66 mm square. Okay, then FC, alpha and lambda, these are given to us in the data. So let me solve the sum first of all using the Ranking's formula. Okay, because they have told us to calculate the load using the Ranking's formula. Okay, so formula stands for FC into area divided by 1 plus lambda square. FC 320, so 320 plus area, that is 42725.66 divided by 1 plus alpha, that is 1 divided by 4800 into lambda square. Lambda is given to us, that is 90 square. Okay, by solving this one I will get the value 5087.33 into 10 raised to 3 Newton. Let's convert it into kilonewton. So 5087.33 kilonewton. So we have solved the first unknown, that is Ranking's critical load. Okay, that is P. That problem is solved. Now we need to calculate, that is length. Now length is unknown to us. Okay, so now if this kind of sum comes, they have already given us lambda, so we can use the equation of lambda first of all for calculating length. So if I am applying the formula of lambda, so formula of lambda stands for, we can say LE by K. Okay, let's try to understand first of all over here. Now problem is with the K. K is, we can say, root of I by, I can easily get the value of I and area for the hollow circular section. There is no problem with one. Lambda is given to us. Okay, so I can easily calculate the value of this one, LE. Once I get the value of LE, that is effective length, and condition is given to me, so ultimately I can calculate the length. Okay, so try to understand sum from this point of view. See, whenever this kind of variable sums comes, hint will be definitely there in the example. Okay, and our hint is only, that is lambda. Okay, so let's start the sum using the lambda's formula. Now lambda stands for LE by K. So right now I do not have the value of K, so first of all I need to calculate the value of K. K stands for root of I by A. We have already calculated area. Okay, now I need the value of I. I stands for minimum of Ixx and Iyy. Now for the hollow circular section, Ixx and Iyy's formula are common. Okay, so let me calculate first of all I. That is, for the hollow circular section, formula stands for pi by 64, capital D is to 4 minus small d is to 4. We have the value of capital D 380 and small d, that is 300 is to 4. Okay, so ultimately I will get the I, that is 625.93 into 10 raised to 6 mm raised to 4. So once I get the value of I, now I can go for I by, see, value of area is over here, we have already calculated this one, 4725.66. Okay, let me just zoom the screen. So now K, root of I by, now I, that is this one, 625, okay, 0.93 into 10 raised to 6, and area, and that is this one, that is 42725.66 mm square. By solving this one I will get the value of, we can say, K, that will 121.04. Once I get the value of K, now I can go for this formula. Okay, so now I am going for the lambda equals to LE by K. Now the value of lambda is given to us 90, L is unknown for us, and K, that is, you can say, 121.04. okay, so ultimately from this one I will get the value of, we can say, LE, that is 10893.35 mm. Okay, and now once I get the value of LE, they have given us the relation of the end. See, they have told us that one end is fixed and other end is free. So now I can apply this formula over here. For one end fixed and other end free, I can say LE equals to twice L. I have got the value of LE. Okay, that is 10893.35 equals to twice L. So ultimately L will be this term divided by 2, say 10893.35 divided by 2, so I will get the answer 5446.67 mm. Let's convert it into meter. That is, we can say 5.446 or we can say 5.45 meter. So this is the example. Okay, see, up to rankings formula, this one our normal sum, nothing new. Okay, but they have given us lambda in this example, and when lambda is given, they have told us to calculate L. So in this kind of variables example, we need to solve sum using this kind of relations. Okay, now next example number 7. Calculate the critical load for a strut which is made of a bar circular in section and 4 meter long. Okay, chalo. 4 meter long is there, so ultimately 4000 mm, which is pin jointed at both ends. Pin jointed at both ends means both supports are hinged, so both ends are hinged. The same bar, when freely supported, gives a mid-span deflection of 10 mm under a load of 80 Newton at the center. Now they have given us a simply supported beam and central load is there, that is 80 Newton. So it gives a deflection. Whenever it is applying, it gives us deflection. This is our deflection. Okay. So what we need to calculate? So for that one, we need to calculate using the critical load. See, now they have not mentioned us over here which kind of load we need to use, either EULER'S load or we can say Ranking's load. But as I have told you earlier also, for the Ranking's load we compulsory need the value of FC and alpha. Now these two terms are not given to us, so we cannot use Ranking's formula. Okay, Ranking's formula can never be used. So ultimately I will get only one case, that is we can say EULER'S load, like this. So okay, so this is the method how you identify that which formula you need to use to solve the sum. So first of all, I will use the Ranking's formula, EULER'S formula. Now the formula stands for pi square EI upon LE square. Now pi is constant, E is E is not given to us in the data, that is modulus of elasticity. So ultimately right now for me E is unknown, as well as I is also unknown for me, because they have told us that circular section, but they have not given to us its diameter. So right now I cannot calculate I, even E also knows there. Okay, upon LE I can calculate. See, they have given us both ends are hinged, so I can say both ends are hinged, so L equals to L. Okay, so that is 4000 mm. So problem of L is solved, but they have not given us any idea about EI. So for that one, what they have given to us hint, that they have told us our simply supported beam is there, 80 Newton force is there applied at the center. Okay, so for that one deflection will occur for this one. Now for simply supported beam, the formula for the deflection is this one. See, for just a minute, simply supported beam with central point load, the formula of deflection stands for y equals to WL cube by 48 EI. So that's the formula which we need to use, because they have given us the deflection. How much? The deflection is 10 mm, that is y 10 mm, load that is 80 Newton. Okay, and E they have not given to us, by mistake I have written over here, E is not given to us right now. So I will use this formula first of all, y equals to WL cube by 48 EI. Now y is given to us, that is 10. W that is also given to us, that is 80 Newton. L that is also given to us, that is 4000. So 4000 cube. Divide by 48 and keep the EI as constant, because EI is unknown for us in the EULER'S formula. So by solving this one, I will get the value of EI, that is 10.67 into 10 raised to 9 Newton into mm square. EI means flexure rigidity. And once I get the value of EI, now let's put down it in the EULER'S formula, because those were the terms which were unknown for us. Now I can apply EULER'S formula. P equals to pi square EI upon LE square, pi square. Now EI, that is 10.67 into 10 raised to 9 upon LE square. LE is this one, for hinge support at both ends, so 4000 square. By solving this one, I will get the value 6.58 into 10 raised to 3 Newton. Let's convert it into kilonewton, so 6.58 kilonewton. Clear? So in this kind of example, always there will be one case regarding this one, deflection. So apply the formula for the deflection and calculate EI, and then put down it in the EULER'S formula. Okay, regarding LE, and conditions will be always given to us. Let me show you one more example like this. Okay, it has not been asked in the example, but this is just a variation. Now example number 8. Calculate the critical load for a strut which is made of bar of a circular section. One more time, circular section is there, length 4 meter, which is fixed at one end and hinge at other end. Okay, and conditions is given with respect to length, no problem with that one. The same bar when freely supported, gives a mid-span deflection of 15 mm. Now deflection is given to us 15 mm under uniformly distributed load of 30 kN per meter. Now this time they have given us load instead of point load. Now this time they have given us UDL. How much? That is, we can say 30 kilonewton per meter, and it will create a deflection. How much? So deflection is also given to us, that is 15 mm. Okay, so length is given to us 4 meter, one end fixed, other end hinge. So for that one, first of all calculate LE, that is L equals to L by root 2. Okay, L is 4 meter, means 4000 mm, 4000 divided by root 2. So ultimately I will get the LE 2828.43 mm. So first problem is solved regarding LE. Now I need EI. As we did in the previous example, we will do the same thing over here. For simply supported beam with UDL, the equation of the deflection stands for Y equals to 5 by 384 into W equals to 4 by EI. Now Y is given to us, deflection, that is 15 mm. Okay, now and then load is also given to us 30 kilonewton per meter. Now let's convert it into the smaller units, because all the other units are in terms of the smaller. Okay, so 30 kilonewton per meter, so let me convert it into Newton. 30 Newton and upon, in terms of mm, meter is given to us, so in mm it will be 10⁻³. So ultimately 30 kilonewton per meter will be converted into 30 Newton into mm. So 10⁻³ will be cancelled like that. E is not given to us once again. Now let's solve the sum. So Y equals to 5 by 384 into WL raised to 4 by EI. Deflection is 15, 5 by 384 as it is, W that is 30, L 4000 raised to 4 upon EI. So from this formula I will get the value of EI, that is 6.67 into 10⁻12 Newton into mm square. Once I get the value of EI, let's put down it into Euler's formula. So Euler's formula, P equals to pi square EI upon L square. Pi square constant, EI is this one, 6.67 into 10⁻12 upon LE, that is 2828.43 square. By solving this one, I will get the value 8224.67 into 10⁻³ Newton. Let's convert it into kilonewton, 822.4.67 kilonewton. Okay, so guys, this was the chapter of column and strut. I hope so we have got all the concept regarding this one. Okay, myself Assistant Professor Gaurang Prajapati signing off.